Good. Well, so that we don't end up delayed, let's go ahead and get started. Welcome to everyone that's joined already. I know a lot of people are still joining, but we'll go ahead and kick this off. To start, I will introduce Cahit Benel from TNO. He's the coordinator of the OUTFOX project, and he will just give a short introduction to the project before we get into the full presentations. So, Cahit, go ahead.
Thank you very much, Erin, and then good afternoon, everybody. Thank you for being in this webinar. I'm not going to take too much time. I would like to just quickly present the fact sheet of the project and then leave the floor to the most important people of this webinar. And then, so the project that we are working on is called OUTFOX, the Optimized Upscale Technology for Next Generation Solid Oxide Electrolysis. So the main mission of this project is to eliminate scale as a limiting factor in the deployment of the solid oxide electrolysis technologies. And then we have approaches like this, threefold. We would like to scale up the size. We are addressing there the cell dimensions, stack dimensions, as well as the module sizes. We are also looking at the high volume and cost efficient manufacturing techniques, how to improve this, and as well as increasing the current densities of the cells, stacks, as well as the modules. So the consortium consists of 9 partners across Europe. TNO is the coordinator from the Netherlands, and also from the Netherlands we have Shell as an end user. If we go to the north, we have Estonia from Elcogen from Estonia, focusing on the cell manufacturing and development. A bit of north, Finland, again Elcogen for the stack manufacturing and stack development, as well as VTT, Research and Technology Organization, focusing on the stack testing and stack testing development. And then going to the south now that we have Italy. So from Italy we have Politecnico di Milano and then Fondazione Politecnico di Milano. They are very active with the techno-economical analysis, life cycle assessment, and then business cases. And finally, last but not least, we have a Link Consulting and Management from the UK, working on dissemination and communication activities. We had a total grant amount of roughly 3 million euros, and the project is supported by Clean Hydrogen Partnership, co-funded by European Union. And then at the moment, we are within our last year of the project, so we are expecting to finalize within the Q1 of 2027. And then today, my colleagues from Elcogen and Convion will share their findings in this project, and then perhaps they will give a high overview of the technology and how they look at it. With that, I serve my purpose, and I leave the floor back to Erin, I guess.
Yes, thank you. Good. So we have a lot more people joined. So this is the second webinar in a webinar series that we're doing for the OUTFOX project that Cahit just presented. So there's another one, a third one in 2 weeks' time. And progressing from the more fundamental research questions that we discussed last time into now looking at the scale up and the stacks that we'll discuss today. And then the third webinar will be more on the economics and road mapping for really bringing it to the market. So I'll put more information up about that at the end. And just a logistics thing, please put any questions that you have in the Q&A box. We'll have some time for questions after each presentation, and as well that the presenters can type questions if there's no time to answer them in the webinar itself. So good. With that, then let me introduce our first speaker. So Jan Grolig is the Chief Technology Officer at Elcogen, where he leads the product development of next generation solid oxide fuel cell and electrolyzer technologies, with the mission of making high efficiency, emission-free energy solutions a practical and affordable reality for the global market. With over 15 years of expertise in electrochemical energy systems, Jan has a proven track record in scaling complex technologies from the lab to commercial production. Prior to joining Elcogen, he held executive leadership roles as CEO and CPO at Stargate Hydrogen, where he oversaw the development of advanced alkaline electrolyzer stacks and systems, and previously served as a head of technology and innovation at Hexus AG. So, Jan, go ahead.
Thanks. Should see my screen. So, yeah, welcome everyone.
You put it in a presentation mode. We see the PowerPoint. Yep, there we go. Perfect.
Very good. Wonderful. So, yeah, hi everyone. Thank you for joining this webinar. Before going directly into the details of what we have been doing in the OUTFOX project, I would like to introduce the topic a little bit broader. So if you look at industrial processes, then usually if you want to decarbonize them, there is a lot of work to be done. And what we like to look at is waste heat, for example. Some people call it waste heat. We like to call it a resource because solid oxide electrolysis technology, what this webinar is about, is the only electrolysis technology which can operate near 100% efficiency with a reasonable output. And typically when you look in the industry, then at electrolyzer companies or even fuel cell companies, you would usually have a company who is doing everything, basically, which is defining a market segment, developing a core fuel cell technology or core electrolyzer technology, build a system architecture around it, manufacture the system, and then do the sales in this targeted application. So presenting the full value chain. That's not what Elcogen is doing. At Elcogen, we focus only on the core technology which is used inside an electrolyzer or fuel cell system. And we do that because we essentially believe that if you want to scale the technology, you need to produce a lot of it, a lot and large, but predominantly a lot of them. And by being application agnostic, using our technology not only in electrolysis mode, but also in fuel cell mode, we believe that we can essentially serve much larger markets, hence enabling our partners and customers to benefit from economies of scale. And just a few key facts about Elcogen. As mentioned already in the introduction, we are based in Finland and in Estonia. Our headquarters is in Tallinn, which you see in the lower picture. We recently inaugurated our new factory last summer, which allows us to produce on a production floor more than 10,000 square meters. And we are long in business, 20 years. We are very diverse in terms of nationalities, educational backgrounds, and we sell our products around the world. As we are working on the core technology, quite brain-driven, you could say. So we have a relatively high degree of highly educated colleagues. And in the framework of the OUTFOX project, or why Elcogen was joining this project, I think it's good to start with the questions: why is it interesting to look at larger stacks and cells at all? Why does it make sense? And I took a look at the latest hydrogen monitor, which was published last year, and you can look at what has happened in 24, which is kind of the status quo. So I will not focus so much on future music, but the as is. And if you look at the most use cases for hydrogen, then it's typically relatively large scale installations. So if we want as an industry to replace gray hydrogen with green hydrogen, then we probably need to find a way how to use this in these industrial settings. And that's where SOEC technology comes into play. But obviously, if you look at the different available technologies like SOEC, PEM or alkaline, then you would relatively quickly see that SOEC stacks are relatively small in size compared to PEM, for example, or compared to alkaline. They have huge advantages in terms of efficiency and in terms of using the waste heat of these industrial processes, yet they are small, and that's a challenge. And hence, it was a strong motivation also for Elcogen to join this consortia, because we believe if we want to really have an impact on decarbonization, we need to get to larger industrial installations, which will require larger stacks as well. Because obviously you can use a lot of scale, a lot of small stacks and bundle them together, which is done in the SOEC world. Yet the larger you have the stack, the simpler and essentially cheaper you can make the adjacent systems. So we try to look at different ways. How would you get to larger stacks essentially? And for us, it very much starts with our cell, so to say. For those of you who know Elcogen, we work with fuel electrode supported cell technology, which means that you have a very thick porous transport layer, and on these you apply functional layers as well as the electrolyte and the air electrode. And we produce this already today at a larger scale. Now, how do you make that bigger, basically? And there is, my favorite starting point, so to say, is an IV curve. I took a random example of a previous research project we have been working on. And of course, most people might know that you look at voltage and current, but I like to translate this IV curve usually into hydrogen output per square centimeter. If you look at the current density at the X scale, you can translate this into hydrogen output. And at the same time, you can translate the voltage at where you operate your cell into the efficiency. And when you then take the cells to build a stack, essentially, you can set your desired outcome of how much kilos per hours your stack should produce, and you can translate this into a total cell area. So the more hydrogen you want to make, the bigger cell area you need. So typically, you take one single cell and combine it into multiple layers into a stack, which then in our case looks like this. And in OUTFOX, we look at two ways how to increase the output of a given stack. The most, I would say, impressive one or most visual one is essentially to increase the cell size. And secondly, within this project framework, we have also in the cooperation with BTT looked at ways how to increase the current density, hence increase the hydrogen output per square centimeter. Which brings me to the framework of the project, where we have, with the Estonian entity, looked at the cell part, and with the Finnish part, or with our Finnish colleagues, more on the stack part in cooperation with BTT. And we had 2 weeks ago the webinar also held by TNO, and there it was also looked at larger cells. And for Elcogen, we have taken our reference cell, which is 144 square centimeters, and we have tried to understand or worked out how can we make the reference cell basically 2.5 times bigger to 361 square centimeters. So we have not done this once. We have produced a number of cells in this project, and we had also to consider ways that it's actually producible within our normal production lines, so to say, so that we do not need to invest heavily into a new factory, as we have just inaugurated our new factory, but so that we are able, or that we would be able to produce them also later on. And so hence the requirement was very much put on how can we develop this with existing equipment. A key aspect in this is basically this thick support layer, which I explained in the beginning. So we had to adapt the production process and the recipes we are using for the support layer. We had to also find ways how to handle and cut these samples. And we had to also think of ways to prevent cell cracking, because you can imagine that these larger cells are actually quite fragile if you do it wrong in that sense. And then last but not least, we have been also thinking into ways how to adjust the printing parameters so that the layers, these larger surfaces, are still uniform. And as shown here on the picture, we have succeeded in doing so. We have a number of cells produced. They are currently, unfortunately, cut into smaller pieces for the testing so that we can use existing test equipment. Yet, we are quite happy about this cooperation. And then, of course, the question is, how would you translate these large cells into also a larger stack? And here it's much more about utilizing the results of the project. And I like to basically look at the fundamentals, you could say, because this is now for us the step to transfer research result into really industrial products. And here we have started actually already the works towards using them. And one important aspect in this context for us is basically design for manufacturing. So I like to look at how can we make the product architecture in a way that it's later on enables lower cost. And here one can compare how much decisions into a product development project is typically done in early phases during prototyping, and how much it influences later the product cost. And it's often so that decisions which are made very early on in product development are having a huge effect on the later product cost. And for this new stack generation, we choose to work quite closely both with our customers and also with our vendors of the components for the stack, because as we produce the cells entirely in-house, we still source stack components such as interconnects or gaskets from external suppliers. So what we're doing, we need very early input in our product development, and we need to do massive front loading on the stack development to avoid a situation where we basically lock ourselves in a design which is later not producible, or which is later not sourceable, or even worse, which no one wants to buy. And to give you some examples where, as we are just a component supplier, we are not having control over the system design, as mentioned in the early slides. There is probably many people can add even more examples to this, but there are a number of areas where the larger stack product requirements later influence how easy or not easy it is to use the stack from a customer point of view. For example, if you look at power electronics, how to set up the number of cells versus the footprint, so that current and voltage are in the range that you can combine that with standard rectifier solutions. Very simple requirements would be like dimensioning. How do we have to adjust the stack dimensions towards system integration volume, for example? It goes on with process interfaces, safety architecture, or electrical safety. All these aspects we like to consider in our product development so that it's later on easier for the customer to use the product. The same goes when you look at vendors of components. The most hated topic when you speak to vendors maybe is tolerances. So we work on means how can we avoid over specifying our components with too tight tolerances, which essentially prevent us to source low cost components. The same is how can we design components in a way that they are matching existing production lines, because we'd like to avoid bespoke production lines, which then require high upfront investment, hence large scale to reach reasonable cost levels. And of course also material availability questions like what materials are we using? Are we able to source enough of that for the scale we foresee? And of course, many, many more. So what is currently ongoing, which is kind of the, I wouldn't say direct continuation of OUTFOX, but like kind of the result of that is that we are currently forming what we call an LSD core group, where we sit together with key customers of us and key vendors at the same kind of working group, so that we make sure that the requirements on the product and the requirements from the components are well addressed in the very, very early phases of product development. Which brings me to the conclusion of my presentation. So that is, so to say, my take-home message to the audience, that our technology is the most efficient electrolysis technology because we're using SOEC. Of course, it's not the only SOEC technology. The project, the OUTFOX project, resulted us being able to develop larger cell architectures, and also, which I haven't presented in depth today because it was mostly done at our partners at VTT, is how to operate our cells at higher current density. And then last but not least is like how we translate the work of OUTFOX into close cooperation with customers and vendor for actually getting the results transferred from the lab into a real product. Yeah, and with that, I'm at the end of my presentation.
Great, thank you very much, Jan. So please, if you have questions for Jan, type those into the Q&A. We have a few minutes for questions.
I would just stop sharing if that's all right. Yes.
I was just wondering from my side, are there limits that you foresee in how high you can push the current density, especially coming from you have a broader view than only the cell itself? Is there a kind of a sweet spot there, or is there?
Well, current density is of course the more current density you have, the more you utilize of your given cell area. Hence, you basically lower the cost if you think of euros per kilogram per hour. So the challenge there is you want to address this in line with your degradation. If you just increase your current density and you don't control what happens on cell level, then you have a very cost-efficient stack in the beginning, but it will not last long enough so that you actually end up in a commercial product, so to say.
Mm-hmm. Yeah, I can see that. Andreas, you wanted to say something?
Yeah, I don't know. Can I also pose a question in the Q&A? either I don't achieve it or it's not possible. So I have to ask it orally. Jan, as you are now constructing a new stack or designing a new stack around the larger cells, do you foresee any differences in SOFC and SOE designs for the cells or the stacks, or would you rather head for, as you have done before, as I assume, to a design that fits both?
So from cost and industrialization perspective, of course, a one-fits-all solution is always preferred.
Sure.
Yet, to be brutally honest, I do believe that we, in the long run, will have slightly different modifications of very similar products. But yes, to answer your question, I would see in the future that we will have a dedicated SOEC and dedicated SOFC product family.
Okay.
But of course, we do utilize a lot of learnings and, as I like to say, cross-pollinate either technology in both directions, so to say. Yeah.
Mm-hmm. Nice. Now we have a few different questions coming through in the Q&A. The first one, first she says, great presentation. And then the question, how does Elcogen manage the stack health and troubleshoot problems once the stack and system is installed at the client's location?
That's a good question. So we don't have like some kind of control center, Elcogen or something, where someone sees all the stacks in the field running. But we typically do work in close cooperation with our customers. What do they see? How do we interpret the results together? And how do we make sure that the stack is, or the stacks are operated in the right way?
Great, thank you. Next question. How do you do the heat integration part with real operating industries? Can you take us through the hardware or process engineering part?
So typically, if you think of the heat integration, then you would provide the waste heat in the form of steam. Of course, you need to consider what's inside the steam. If you have a lot of waste heat available, but the steam is very impure, then you would need to kind of make sure that the steam is cleaned. But that is kind of the most common way how to get the heat in the system. But I believe this could be also a good one for Tuomas later on when he's presenting the system.
Yeah, sounds good. So please, I'll mark that question as answered, but please ask it again if needed. Then I think we have time for maybe one or two. So what is the biggest limiting factor to scaling the size of the ASC cell to say 1 square meter? Is it the architecture of the cell or the choice of materials?
I would say it's yield. If you make the cells very large, then you run the risk that you break them more easily. And it has to do with the processing, how the materials behave while they're sintered, and how do you make sure that you get a lot of healthy cells out of your process?
Mm-hmm.
So it's not the material, but it's more the processing and the yield, which is the limiting factor.
Mm-hmm. Good. I think this will be our last question. Regarding cost reduction, I see that you mentioned costs related to power electronics, sizing, safety, architecture, etc. You also work on reducing costs at the level of the single repeating unit, for example, in the cell itself or the interconnect materials. Is there much room there?
So if you look at the cell, then it's typically finding ways how to process this cheaper, like finding means how to use less energy to sinter, and also less labor, so to say, how to handle materials in an efficient way. If you look at the single repeat unit, like interconnects, gaskets, and these things, there is some processing involved, which can be optimized, but there are also material choices to be made, which will have an impact on the cost. And I can say we work on all of these aspects. So yes, there's of course, besides making things larger, lasting longer, we have a clear mandate within the team to make it also cheaper.
Mhm. Great. So that's all the time we have for Jan. Thank you very much. If you still have questions for Jan, please feel free to put those in the Q&A and you can always type answers.
Thank you.
Good. Then let me introduce our next speaker. So Tuomas Hakala is the co-founder of Convion, a Finnish pioneer in solid oxide fuel cell and electrolyzer technologies. Having spent his entire career in advancing energy technology and with nearly 2 decades of experience in the hydrogen and clean energy sector, Tuomas has played a key role in turning high-temperature electrochemistry from research into industrial solutions. He's recognized for advancing the commercialization and scale-up of Convion's SOC platform, forging global partnerships, and driving flagship demonstration projects across Europe. Tuomas frequently speaks on energy autonomy, industrial decarbonization, and the pathway from pilot projects to gigawatt-scale solutions. And we're very happy to have him here today. Go ahead. And it looks like you are on mute still.
I believe so. Okay, hello everybody. Thank you for the introduction and thank you, Jan, for an interesting presentation. I see that we look at the same things but from slightly different perspectives. My name is Tuomas Hakala. I'm a co-founder of Convion, and today I will be discussing about aspects of scaling up the SOE systems to meet the requirements of industrial hydrogen applications. You could also maybe take part of my presentation as a call to action, because we are a stack agnostic systems company, and we want to work with the leading suppliers of cell stacks in the world, 2 of which happen to be present here today. And it takes a joint effort to make it to the scale and actual industrial commercial applications. In the OUTFOX project, much of the focus, particularly so far, has gone into exploring the pathways of how to scale the cell or further on the cell stack larger. And we, as a stack agnostic company, we welcome these developments warmly. Our activities in the project are, you could say, twofold. On one hand, we are conceptually exploring pathways to scale with the systems, sort of asking the questions why, how, and what needs to happen, and what are the possible dimensions of advancements that will take us there. And on the other hand, an activity that is about to start very soon, we are in the last year of OUTFOX project, is the system level demonstration of Elcogen's stacks, current and development versions of the stacks in our 250 kilowatt system platform. The demonstration scale will be somewhat reduced to give us maximum flexibility in terms of increasing gradually the current densities as is in the scope of the project. First, few words about Convion. As mentioned here, we are a systems company. The company was founded in 2012, but the history of the team dates back to early 2000s when Wärtsilä Corporation started investigating solid oxide technology for fuel cell applications, specifically distributed power generation in industrial and commercial applications and marine auxiliary power. It was all fuel cells back in the days. That was also when we kind of crystallized our position and area where we could excel or win most. We wanted to be connected with the leading providers of cell stack technology and focus on system technology. And what we understand by system technologies is it's about process, about integration, process control, power conversion systems, product interfaces towards the application, and then the application know-how. After establishment of Convion, taking the activity out of Wärtsilä, we sharpened the focus further on to fundamental technological choices and architectures that can then be scaled for the purposes of industrial applications. And late 24, Convion became part of HD Hyundai. On the right-hand side, you see our laboratory. We have always been out there and drawing the insights from actual use cases, actual environments, or customers' issues and problems. Here you see Arctic and tropical installations, you see marine and industrial biogas applications. This is very heavily affecting our design and productization intentions. As mentioned, the technology can and has and will be used in both electrolysis and fuel cell application. Most of our history, we have worked with fuel cells, and recent 5-ish years with electrolysis. We started with the position that fuel cells are valuable for industrial and commercial users, where you can stack multiple value aspects of reliability, autonomy, heat recovery, etc. And on the left-hand side, you see our current fuel cell products. It's a 60 kilowatt all-in-one mini CHP system. On the right-hand side, you see very similar looking system, and you can say it's a 70-75% the same. Technically, there are a lot of similarities today, and we can demonstrate our system concepts in electrolysis with this, what we call a piloting platform. 250 kilowatt is the electrical input of this system that can be configured for both simple steam electrolysis or reversible, and it can also include the co-electrolysis option. What makes solid oxide technology, and this is something Jan already touched upon, particularly attractive is, well, there are multiple aspects, but the fundamental one is the very high electrical efficiency, specifically when we can use excess heat from another source to generate steam. And this, if so, and that's the case in many power-to-X applications, the process that consumes hydrogen produces excess heat coincidentally with the demand of hydrogen, and therefore we can come up with roughly 30% advantage, 30% less electricity per unit of hydrogen produced when using waste heat for steam generation. And then other aspects I mentioned, flexibility. Compared to other electrolysis technologies, solid oxide electrolysis can be very efficiently and broadly part loaded. And it can also switch into power generation mode if needed, extending the flexibility range even further. And when integrating with a source of captured CO2, we can produce in this synergistic process syngas, and to some degree adjust the composition to meet the downstream next step process requirements for gas composition. This saves particularly in capex, but also in energy expenditure. Here are just examples of the major segments of this green chemistry that we all hope to see and need to see emerging, requiring affordable hydrogen. And many of them, if not all, have the possibility of capturing excess heat of the process. The question why we scale things, we need to start with why, and it's obviously the demand. The illustrated examples there roughly determine if we want to co-locate electrolysis with the demand of hydrogen with an industrial facility consuming hydrogen. I would say at minimum we're talking about tens of megawatts of capacity, but often far beyond that, and that kind of defines the demand and usable building block. This is an inherently modular technology, but there are advantages both within the module as well as at the installation side of reducing the number of units and reducing complexity of the installation. And what we want to come up with is competitively priced hydrogen. We can choose a location to get lower electricity prices, but other than that, what we can influence is a high efficiency, which is kind of like part of the DNA of solid oxide technology. Maximize productive hours per year, stack value streams, and focus very much on installed system capex and not just the core. Specific means for reaching the low cost hydrogen with relating to solid oxide is the thermal integration potential that we discussed about, bidirectionality if there is a possibility of flexing the demand of hydrogen, module scaling, and ease of integration. This is turns out to be also a very important factor. Now, these are two somewhat hypothetical curves of levelized cost of hydrogen using 50 euros a megawatt on the left-hand side, 50 euros a megawatt hour electricity price on average, and different capex. And you see that electricity expenditure, price plus efficiency, both affecting it, has a very significant effect, and the capex levels, while different, that has a smaller influence. This tries to incorporate the module plus the necessary OPEX in it, but not necessarily all of the side costs. Whereas, yes, electricity prices are very influential. However, given the highest efficiency conversion technology, the higher the cost of electricity, the bigger the gap of advantage compared to low efficiency technologies. Yeah, just to summarize the items, since energy expenditure is so important, high electrical efficiency is something not to be traded off in any case. Heat integration plays a major role. It's roughly 1/5 of the total energy input is in the form of heat. High productive hours, we see the reversibility of this technology as a very important means to cap the price of consumed electricity. If we can instead maximize operating hours per year by producing electricity for which we can use alternative fuels, not just hydrogen. And then extending factory manufacturing beyond just the system module to make it a modular factory manufactured plant. Our perspective regarding stacks, of course, for us, stacks are components. They are the most significant individual cost item. Of course, the further we go down the cost trajectory. Also, for example, power conversion plays a very important role, both in terms of performance and cost. But something that we as a stack agnostic company have very much learned over the years, having worked together with multiple providers, is that the interface cost and the interface architecture matters very much. You could say that there's a balance of stack, whatever goes together with a stack has to be kind of accounted as a cost of stack. There's no way going around it, and therefore ease of integration of stacks matters very much. I think we could draw parallels with other modular or cellular technologies such as solar or batteries, where you integrate a very large number of relatively small individual identical units, and ease of integration there matters tremendously. And what is important is that the competitive advantage when it's based on the high efficiency, that can be traded off for reduced capex, because the multiplier effect is so tremendous. In OUTFOX project, the sort of mission that we set to us, it was to remove scale as a limiting factor. One particular reason why I like this project is that it's very exploratory. We don't need to avoid failure. I mean, to succeed, we want to explore different dimensions of advancement and operate the system gradually towards higher current densities, for example, to see where the actual limits are and how do we see them, and what are the trade-offs of different operating points. Here is an illustration that even relatively small individual aspects of scaling, the footprint, the length of the stack, or the current density, they add up to a very significant increase in overall capacity per interface. And that interface cost is important for us. It's also a matter of reliability. And you could say that not reaching exactly all of these, if we only come up with 8, multiplier 8, that's already a very significant step forward. System side, why to scale? Well, cost is a very important factor, cost of manufacturing, but also cost of installing multiple units. It's a modular technology. For many of the hot core structures and enclosures and many of the components, you could have this, in the industry, we have this rule of 0.6, sort of a scale coefficient. When you scale capacity from V1 to V2, this is the experimental thumb rule of how you reach the specific cost of the unit gets relatively less costly as long as the alpha, the coefficient, is below 1. This applies to many things. And you can draw these dependencies for various structures. But what is also very important is that we keep this as a factory manufactured, standardized and configurable product, because in larger volumes, the volume effect of factory manufacturing starts to outweigh the benefits of scaling. And we want to also consider the logistical hurdles of getting things installed and delivered. Today we have this proof of concept scale, 250 kilowatt module. This is at the moment sitting in VTT's Bioruki experimental site, and soon we'll start the OUTFOX system tests. This is also same or identical systems are in multiple locations in the world at the moment, being tested in integrated applications. Those are learning experiences for us. Alongside, we are developing, and this is also part of the OUTFOX consideration, defining and developing a building block of a megawatt scale hot core module, and a concept where multiple of those will be grouped together with certain auxiliary systems and configuration alternatives to make a repeatable unit of 45 megawatt SOEC. This can also be configured as a co-SOEC or RSOC or SOFC system. And in the modular concept, we have interfacing functions also in factory manufactured modules. Finally, when we are at sufficient scale, flexibility of an asset flexibility of a system becomes an asset itself. And building flexibilities in the demand side of hydrogen, we can become good energy citizens of the system, participating in the flexibility markets, generating secondary revenue streams, and overall enabling deeper penetration of renewables in the energy system. This gets me to my final slide about conclusions. Energy efficiency and co-location with thermal sources is a very determining factor. Industrial applications require multi-megawatt repeatable units. That is a scale that needs to be achieved, but not necessarily very much bigger than that. And then in the levelized cost of hydrogen, the non-energy inputs, energy inputs being the kind of most determining, but the non-energy inputs, capex of installed system, utilization rate, and alternative value streams are equally important. Integration is a key at the stack level, system level, and plant level. That's kind of a common thread across the scales. Thank you very much. There you see actually the unit being delivered to VTT test site within OUTFOX.
Great, thank you very much. So again, please put your questions in the Q&A and we can go through those. Great, so one has come in. Very interesting presentation. So integrating biogas into an SOEC system is a very interesting application for syngas. Most of the SOECs currently use nickel zirconia or nickel GDC based catalysts. How do you manage trace impurities in the biogas and save the cells from degrading? And then a follow-on question, is there a significant cost involved in purifying the biogas before it enters the stack? And how much % does it contribute to the overall balance of plant cost?
Okay, that was a multifaceted question.
And I can reread if you want.
Yeah, well, biogas is one of my favorite topics. We've done quite a lot of work with biogas in SOFC field, and as you know, any level of, let's say, sulfur, which is always in biogas, is detrimental. Then the hardest question is, okay, so how much is clean and how clean is clean enough? And we tend to approach in actual industrial installations kind of stage-wise. Its most competitive or most cost-effective approach is that you have a bulk cleaning, which is cheap and sort of stabilizes the impurity levels to a low level already. And then we have a fine cleaning, which is extremely sensitive and robust in arrangement. Now, unfortunately, I can't say the cost of that, because it's also very much dependent on scale. But if biogas goes directly in the system, it needs to be at the ppb level, clean from sulfur-bearing compounds. I think you said integrating biogas with electrolysis, SOE. There is a concept that we've been working on where we actually produce hydrogen to upgrade biogas. Biogas is usually approximately 60% methane only. And if you can produce hydrogen to upgrade that, then you nearly double your amount of biogas, amount of methane that comes from a given source, and biomasses are by nature distributed. It's an interesting application, and their biogas does not directly go through our system.
Okay, great, thank you. Then there's another question. Can you elaborate on what is a good stack interface for good integration?
Yeah, we particularly in the old days when we were starting this, we understood that many of the stack developers very much looked from inside out, and stack interfaces were probably considered for a system of a single stack. Like there's a stack that somehow maybe it was designed for the test bench, and it was easy to do. But in our systems, we've always had tens of stacks. So the number is just a number. It's n. It could be anything, and the choice of how many depends on other things than or it should depend on other things than the ease of integration. Usually, compression requirements are something to consider very thoroughly in a multi-stack system. Those tend to be sometimes complicated, and the compression mechanisms, if there is a high level of compression needed, they tend to be fairly difficult to arrange. In our there are different types of stacks. Sometimes there's a piped inlet for air, and sometimes there's an open like in soft mode, open cathode for air. Considering integrating these open air approaches in the stack design helps a lot. If it's only something that we need to start thinking once we receive the stack, then that usually is not the optimal solution. This is of course very abstract for someone who's not familiar with stack designs, but maybe those are a couple of aspects.
Great, thank you. We have maybe 2 more minutes. You mentioned, you touched briefly about reliability. Do you have any insights? How do you do that at higher scales? Is it on a module level, or how would you tackle that?
Reliability, I would say that longevity is maybe the most important pain point usually with this, rather than lifetime in general. It's if we have an architecture where stacks are maintained in equal conditions and the integration is done well, we usually see very steady aging of cell stacks along the same pathway. And then the question is the degradation rate too much for a commercial rate? But we don't see that much of individual stacks failing, which is necessary, because if you want to couple a lot of things together, and single point of failure would mean stop of production, then that's a major issue. In terms of system reliability, our approach has been to simplify the system to a bare minimum. We have removed the sort of usual culprits of unreliability as much as possible, and simplified overall the system architecture yeah, that we have a handful of major components, and that's it. And that's our approach towards reliability issues. We have also excluded from the core module such functions that would typically require, for example, frequent maintenance interventions.
Okay, great. So that's all the time we have for Tuomas now. Tuomas, there are a couple of questions in the Q&A still. If you could maybe type your answers to those, and they
Thank
can
you.
still be addressed. But let me go ahead and then move on and introduce our final speaker. So Andreas Mai is the technology manager for SOEC and Power to X at Topsoe, where he drives the development of high-temperature electrolysis solutions and their integration into Power to X systems to enable large-scale, flexible hydrogen and synfuel production. With 25 years experience in solid oxide cells, Andreas brings deep expertise in solid oxide technologies, high-temperature materials and degradation mechanisms, and electrolyzer system integration. He spent 17 years as CTO at Hexas, leading their development and manufacturing of SOC stacks and components, and earlier completed his PhD in postdoctoral research at the Research Center Jülich, working on SOFC air electrodes and degradation phenomena. So we're very privileged to have Andreas here to share Topsoe's perspective on SOEC technology readiness, materials, challenges, and also the lessons that they've learned. Andreas,
Thanks
go
a lot,
ahead.
Erin. Yeah, and thanks also to the other speaker. Like, I'm a little bit the OUTFOX here because I'm not part of the OUTFOX project, or Topsoe is not part of the OUTFOX project itself. But I'm going to show, I think, things that have been said before by the other speakers also, and then also say things that we maybe see a little bit different. So I think it fits perfectly in what we saw before and what we will see now. Concentrating mainly on our system design from Topsoe for the solid oxide electrolysis. And then also looking a little bit into the manufacturing activities. So a short intro to Topsoe itself. We are around 3,000 employees, mainly based in Copenhagen, but then also spread out all over the world. And we're coming from the chemistry industry as a catalyst manufacturer, but also with system design to build, to synthesize methanol, ammonia, also sustainable aviation fuel. Yeah, what makes us a little bit special, I'm always showing on this slide here, like we all want to make out of renewable energy green hydrogen with solid oxide electrolysis, or with other electrolyzers maybe even. But then especially with solid oxide, it is very beneficial to utilize it then to synthesize downstream chemicals like ammonia, like methanol or similar. And what makes Topsoe a little bit special there is that we have a huge background in nickel-based catalysts. Yeah, with knowing many degradation mechanisms that you see for nickel-based catalysts when you expose them to special gases, let's say. Then we have also a history of Topsoe fuel cells where we have nearly 25 years of, or started 25 years ago on working on solid oxide fuel cells. Then we had in between a small phase where we had only a small group working on solid oxide electrolyzers. And we've now started the business again, concentrating really on electrolysis. So we are not looking on fuel cells right now. I don't know if we will ever do with the current hype in fuel cells, it might be, but we are really looking on electrolyzers. And we also have the downstream processes in our house. That's really in our DNA, ammonia, methanol synthesis. And the coolest way to actually combine the two is then to build SOEC stacks, to build cores out of it. And then also we've built up a production plant to produce SOE stacks. Yeah, looking at the concepts that we're following, So for Power-to-X, as I said before, we think together with others that solid oxide is especially valuable if you have downstream processes, and then even better if you have downstream processes that have leftover heat. So there, especially green ammonia is relevant because here you can feed the electricity, the heat that you generate in the ammonia loop, you can feed back to the SOE, and that then really boosts your efficiency if you compare it to low temperature alkaline or PEM electrolyzers. Same goes looking at green e-fuels. Here I have one route showing that you can combine an electrolyzer then with an electrified reverse water gas shift reactor, which we also have in-house. So here you would actually run the SOE only to produce hydrogen, combine it with CO2, and then you go to a Fischer-Tropsch synthesis and would produce here, for example, sustainable aviation fuel. There is also other routes to do that, and I'll show that in a future slide. Then we have green methanol. Here you don't have so much leftover heat in the synthesis of the methanol, but we nevertheless think that you can also use the higher efficiency of solid oxide in here, especially if you have leftover steam from somewhere else. But also without that, your efficiency will be definitely higher than if you use alkaline electrolysis or something similar. Same goes then also for green renewable methane. There you also have leftover heat. And then if you want to make it super complicated, you can combine it all together and then even make proteins out of it by combining it with a biological synthesis. That's what we're actually doing in a very small project, or in a small project that is funded by the Gates Foundation and the Novo Nordisk Foundation. Here we combine CO2 electrolysis and together with hydrogen electrolysis to produce methanol. Then we have the aim of synthesizing also acetic acid in here, and then combining it with ammonia synthesis to produce protein here. But this is really done at a very small scale until now. And the question is really, do you want to produce protein like that instead of doing it the normal agricultural way? And then we have a newly started project where we also work together with TNO and Link, called Sapphire. That has just started 1st of January this year, and we had a kickoff meeting at TNO just a month ago. And this looks at combining co-electrolysis, so simultaneously electrolyzing CO2 and hydrogen, sending that to a Fischer-Tropsch reactor, and then making sustainable aviation fuel in there. Here we have as partners TNO, as mentioned, Link, but we also have CEA in there and EPFL, also Aarhus University and us. And then we have as a potential downstream provider, SOEL in there. Very happy that we actually got that project. Was a huge competition. And here the whole thing is that CEA and TNO, they will provide cells that are optimized for co-electrolysis, and then we at Topsoe will combine them in a small pilot that makes solid oxide electrolysis, co-electrolysis, combine that with a Fischer-Tropsch unit from SOEL that is even smaller, and have that all on the side of Aarhus University where there is biogas production and similar on site. We currently see the first route to go for SAF rather producing hydrogen, but we see definitely efficiency advantages going to co-electrolysis. So we see it rather as a future route than as a today's route, but it surely makes sense to look into that. Looking at system designs, you can see here that we go at Topsoe all the way actually from nano to mega. So maybe a little bit in contrast to the two other speakers, we really want to cover it all, going from electrodes till SOE sections. But what we don't want to do is actually have one stack that can do it all. We really optimize the stack to do electrolysis, and not so much optimized, or actually not really working in fuel cell operation. And then if you combine that all to a plant, that is what a 100 megawatt plant would look like. I'll look at the manufacturing processes later on, but we kind of stole the idea of making it in these containerized or container fitting solutions from the other part of our company, because that is how Topsoe currently designs and builds green methanol and ammonia plants, where all of it is actually built up of these kits that can then be produced in a series manufacturing style and be truckable and transported on site, and then finally fixed or assembled there on site. Yeah, looking in more in the green ammonia, green hydrogen part of it, that's how we planned that it looks then in an SOE part of it. So we also combine 4 of these cores in one section. So then we are, as Convion has also proposed, at a 5 megawatt scale, approximately, because each of that cores contains 12 stacks and has a capacity of around 700 kilowatts, so close to a megawatt. So combining them 4 together also leads to that 4 to 5 megawatt that we see as one building block here. And then we combine several of these building blocks together in a plant. And that is then a rendering how a 100 megawatt ammonia plant will look like, which we are currently designing and planning with one of our first customers, which is First Ammonia. And then if you look at it, then that's how a 100 megawatt plant would look like. And the 300 megawatt plant would then just be a multiplication of 3 of the plant. And the 500 megawatt plant would then even look better, larger compared to that. We also thought about how can we actually do maintenance on the SOE part of it. And there we look mainly in how can you replace stacks or other components in the solid oxide electrolyzer core. And we are then taking the cores out of it. You can see how that is here done with a forklift. Take that to a workshop, and then you could do exchange of hot balance of plant components or exchange of stacks in a workshop dedicated, made for it, and not within the plant itself. That's just another example how then a green ammonia plant looks like. Here we don't have a solid oxide electrolyzer built in. Here it's a conventional alkaline electrolyzer that is standing in Denmark, but it's combined with our ammonia solution here, and is had been built up last year and had the first running hours since then. So here we're mainly demonstrating a dynamic ammonia plant combined with an electrolyzer, and in the future that would then be replaced by the solid oxide electrolyzer. Not in the plant, but in the concept. Looking at manufacturing, I think it's very important, if you think about manufacturing, to think about how many parts for a 100 megawatt plant would you actually need to build. And it's fully clear that for the electrode layers, you need to build or manufacture millions for a 100 megawatt unit, while for the cells, it's then a few 100,000, while for the stacks, it's only 2,000 stacks that you approximately need. So that actually needs your production philosophy must also be a little bit different. Here it's mass manufacturing. Here it's also mass manufacturing with highly automated manufacturing. Here for the stacks and modules, it's series manufacturing. So we still think highly automated makes sense for the stack, a little bit less for the modules. But then it really goes down if you go to the cores or a multi-stack assembly and to the section where you see the numbers really go down. So here we are rather collaborating with suppliers that do rather a series assembly or a small series assembly rather than having a series manufacturing. So that is more closer to, I don't know, maybe manufacturing of a car or manufacturing of a heating device or something that is done in these numbers normally. Yeah, and then finally, the plant is one of its kind at 100 megawatt scale. So there, it rather needs prefabricated modules that you can then set up with a plug-and-play architecture. Yeah, we've shown that several times before. That's our stack manufacturing plant in Herning. One of the biggest in the world with 500 megawatt capacity per year. And we inaugurated that last year. A little bit a look inside here. The first production lines, automated production line, became operational last year. We had the official inauguration in October last year, and now we are still in the run-in phase of the factory. So taking that picture from before again, but now with real life pictures. So we have built real electrodes, we've built real cells, we've also built real stacks, integrated them in a real core. We are currently building a 2-section setup like that at our plant in Frederiksund, which will be running this year. So we have realized nearly all of it, and then first customers are probably putting the final signature under the contracts this year, and then the first plants will be running in 2-3 years. Yeah, little bit on the validation on the core. We have built up one single core in Frederiksund at the plant, mimicking a small green hydrogen unit with 350 kilowatt electrical input. And I think I've shown that before. With total 11,000 hours of operation now, and you can see we've gone for some straight line operation in the beginning, then some dynamic operation to show how fast can you actually modulate. And now we had to run with a slightly reduced output in the last few months because we were waiting for stacks that we get in sufficient numbers from our Herning plant to integrate them into that demo. Yeah, we've been running it for 11,000 hours, as I showed before, in total. This is looking mainly at the operation phases in the beginning. So we ran for 2,000 hours straight line, seeing only a little bit of run-in degradation, but then not much more degradation in the end. Then we've operated dynamically to demonstrate how fast you can actually switch off or switch on a solid oxide electrolyzer. And I think in contrast to what has been said many times before, so I don't know, 5 or 10 years ago, we demonstrated that solid oxide can be sufficiently dynamic to fit to a renewable energy scenario with 3 minutes from 100% to 0%, and then 3 minutes again back to 80%. And the main limiters here are, as you might all know, not the stacks in itself. It's rather the balance of plant that cannot adjust the flow fast enough, or heaters that cannot react fast enough here. So that's very well fitting to the downstream processes. Also, an ammonia plant is not much more flexible or fast here. So we think solid oxide can also be operated dynamically, and that's very important for our customers at least. Yeah. To summarize, we've shown high efficiency. We've also, we think for us, it is vitally important to combine it with front end and downstream processes like ammonia, methanol, or soft synthesis. And we've shown that it can be operated dynamically. And then one of the most successful projects was actually this building block that was presented to our employees last year, where everyone could build up his own electrolyzer at home, even together with the children. So open for questions.
Thank you much. We should have known about the Lego set. We could have sent that to participants. But good, yes, so please include your questions in the Q&A. There's one that's come through already. Have you investigated the impact of ramp rates on degradation?
We have investigated that, and there will actually a paper coming out from a PhD student that is at Aarhus University. We have until now not seen a clear impact of it, I must say. As long as you choose your ramp rates that the the temperature gradients are not too strong, then you don't see. I think if you would do the ramps very slowly, that would actually be the most critical. So if you really run through the endothermal range of operation, that might be, but we have not tested that.
Okay. Great. And next question, they say very nice presentation. The SOEC can also work for CO2 dry or nearly dry electrolysis?
Yes, we've had that actually in a in between time as the only electrolyzer product. Dry CO2 electrolysis, we are right now not focusing on it, but we know we can do it. We have also a test rig that is still from the old days that is running on dry CO2 electrolysis, and that's running for 14,000 hours now with one single stack in there. So it can be done. We've not seen such a huge customer interest yet. We see customers that are interested in it, but the hydrogen, ammonia, methanol market is just much larger.
Okay, thank you. And next question, how much does sweep of the oxygen electrode influence degradation?
Yeah, interesting. Interesting would be to know who it is. Maybe he could also write his name, then I can maybe talk in the future also a little bit about that. It depends what comes with your air. Like we have one site that I have shown in Faulum that is really on a biogas site, and there we sometimes get sulfur components in the air. Then you would rather want to sweep as low as possible. If you have huge humidity in the air, you might also not want to have too much water on the oxy side. So I think it influences, but if you take the right measure, then it should actually not influence too much. It is more than impurities that you would bring into the system. And I think you could also in operation just produce pure oxygen. That has also been shown before by universities that you can do it.
Okay, thank you. Okay, next question. Have similar long duration tests been performed in the co-electrolysis mode? Can we achieve similar degradation rates with water electrolysis, or will it be higher, and why?
Ah, Venkatesh, very nice. Nice to have Jan, me, and Venkatesh in one call. We've not done that until now. We've done it a little bit on our old stack platform, but not for very long times. And that's something that we actually plan in the Sapphire project, that we will also look into long duration tests with co-electrolysis, where we target 3,000 hours at least operation in co-electrolysis. Maybe we can also go for longer. Let's see together with GNO and CR where we land there.
Sounds good. And if any of the other panelists want to also comment, that's totally fine as well. Good. And maybe another question. We have a few more minutes. How do you see the different routes to the ESAF in comparison?
Yeah, I think probably right now the easiest is to produce hydrogen and then have reverse water gas shift and go to Fischer-Tropsch. But I think the more elegant and the more efficient is to go for what we're doing in Sapphire and combining co-electrolysis then directly with Fischer-Tropsch. I see a little bit of challenges when you look how the tail gas then will consist, and also heat exchangers that might have some issues with carbon formation. But I think it's solvable issues that we just have to tackle in the project before we make a product out of it.
Thank you. Jan or Thomas, did you want to comment on anything?
And now finally a cost question comes.
Yes, as I can read that for you. Since Topsoe is in the megawatt level scale, is it a cost of below 500 euros per kilowatt possible in the future?
Yeah, the question is, what do you mean with euros per kilowatt? Do you mean the whole system, including a downstream ammonia, or is it just for for the system? Yes, I think it's possible. I think it is, at least from what we see, it should be comparable to what we see right now for, let's say, Chinese or European alkaline producers, and we can end up in the same range. But I definitely think in the first years, our benefit on the LCOH regarding efficiency is what compensates the higher capex we will have in the first years. And then in the end, such numbers are possible. Yes.
Quick comment regarding that. I think in SOE circles, we should stop talking about euros per kilowatt. We should talk about the output instead.
Yes.
Because there's a clear difference.
Please, thank you very much.
Thank you.
Good comment.
Yes, very good comment. I'm saying that also all the time. The question is, people say euro per norm cubic meter or euro per kilo per kilogram per year or something like that. We need to agree on a figure that people get in their heads also. Like we're also always saying a 5 megawatt plant. Actually, you should speak about a 10,000 norm cubic meter plant or metric tons per day or something like that's what they use it for an ammonia plant. They're not saying how much natural gas does it consume. They're saying how much does it produce of what you want to have.
I totally agree. We need a European sort of a harmonized term to compare things with.
Yeah.
Yes, great. Good. Maybe the last question. How do you treat the replaced or used SOEC stack? And are there any reusable components available?
Yeah, we have been looking into that a little bit, and then we've also been looking in the funded projects that are there. Like one large one was in Germany that looked at how can you recycle components. We don't have a very clear concept there yet. But it surely should, like if you look how large the plants are, you need to have a concept in the future how much you can recycle.
Great. Thank you very much. Good. So that brings us to the end of the webinar. I'm just showing one slide here to promote the third webinar that will be in 2 weeks' time. There's a QR code you can scan to register directly. And also just wanted to say, if you have any further questions that you would like to ask any of the panelists that we've had today, you can get in touch with us at outfoxproject.com. You'll also receive an email just with some follow-up that will also have an email address that you can send any further questions to, or if you want to be put in touch with anyone. And of course, you can sign up for our newsletter to hear any further results coming out of the project and further events such as this one. So with that, I would just like to thank the speakers very much for your time and your willingness to present and participate, and especially for Andreas being our guest speaker, not from the OUTFOX project. It's really appreciated that you joined us today. And I hope everyone has found it interesting and learned something from the webinar. So thank you, everyone.
Thank you. Have a nice